Hey, John here. I'm talking about these Verilog examples today, the PLL subdirectory, where I've got two examples and some notes on how to go about using these things. As always, thank you to all the Patreons, especially the VIPs listed here. All right, so get oriented. We got these Verilog examples. Let me open up this tab here because we can look at some documentation that is linked to in here. So this is the main, top level repo directory. There's a link to this thing in the description below on YouTube. This is a link to the playlist that this video should be part of. The ICE40 Fpga docs can be found here, and you click on this sucker right there. You end up in lattice land of the LPHX, and in the bottom of a lot of stuff, there's a bunch of links down here, and this is what we're looking at, the PLL design and user guide for the ICE40 and the technology library. I've shown you at least this before in this YouTube series on my channel, so we're familiar with that already, but we're going to use it for some reference material today and have a look-see at the design and user guide for the PLL that's inside of the Fpga. So let's first of all understand what the heck is a PLL. PLL stands for phase locked loop, and it is an analog device that is inside. I don't know any FPGAs that don't have them. What they do is they take a clock, a free-running clock frequency, and they allow you to use a voltage-controlled oscillator and some counters and things like that to change the frequency. Effectively, you can multiply the input frequency by some number and then divide it by a different number, which gives you essentially a rational number that you can use as a coefficient on the clock arriving in the Fpga. There's a lot of constraints. You can only go so fast, you can't go so slow, and so on, but within a reasonable bound of what you'd want to do certainly as a hobbyist, this is a pretty reasonable thing to do. Okay. What do we got here? The clock PLL, introduction, routing, resources. Now, when I first learned how to use this thing, you could say I still am learning how to use it. This is like one of the simplest PLLs I've ever used, the simplest FPGA I've ever used, and yet it still never ceases to amaze me how many pitfalls you can get into while trying to make it go. So I'm going to show you a couple of things. I'm going to discuss some mistakes that I've made, and obviously others have, based on the morass of people asking questions about it on the internet, just so you can get over the smallest of entry-level hurdles and just get the basic thing to go. And 9 times out of 10, that's all you ever want. Especially if you're a hobbyist. I just want to have a 65 megahertz clock. Show me how to do that. Don't make me read 200,000 pages that don't even include some of the constraint information you need to know, which is hard to find. So let's dive right in. I'm going to bounce around a little bit before we get there because of these dependencies and things like that. So it may require that you read this document twice before you understand what's going on, all right? Luckily, it's only 36 pages. It's not too bad, okay? So what do we got in here? A bunch of table of contents, blah, 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 name of things. Introduction, technical note discusses the clock resources. And again, they're talking about clocks. So this is how you generate a frequency that runs at the speed you want it to. It tells you how many there are in the various chips. I'm using an HX4K today, and it has 2 PLLs in the package that we're using, which is the 144 ball TQFP. There's another typo that you'll see them correct in the future at some point, because these don't have balls. They have gull wings, right? Okay, moving along. We got 2 PLLs that we can use if we want to. They talk about global routing resources. I'm like, well, why are we dealing with global routing when we're dealing with the PLLs? Why am I so confused? Okay. The reason we have the PLL is so we can generate a free running clock frequency that 99.99999% of the time will be used to clock a synchronous design that you implement in your FPGA. So they've optimized it for the most likely use case. And that is, you want to generate a square wave with a 50-50 duty cycle that goes into a global buffer, which means that it goes everywhere in the entire FPGA so that any of the LUTs, any of the circuitry that you want to design can easily get access to it with the least amount of latency and skew when you were thinking about the clock arriving at all the different circuits inside here, the thousands of LUTs in there. You do not want the clock to be going up and down at a different time for one LUT versus another LUT. It can be very, very bad and inconsistent and difficult to debug your circuit if that happens. Therefore, one of the most common things to do when you're done with your PLL is to connect it up to one of these global buffers so you can route it everywhere and use it pretty much without even thinking about it, without having any problems. Now, they talk about, you need bank 0 and bank 2 and blah, 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 and then they never really tell you that much about why, and they never really tell you specific pins, and this is the part that drives me nuts, and it's a flaw in the design of my FPGA test board that I'm using for this, and others that I've seen other people deal with. It'd be nice if somewhere they would just tell you which pin numbers, or at least the signal names, that you need to use when you're connecting up your PLL. Obviously, I'm still frustrated from what happened 6 years ago when I started that project. In any event, okay, so the difficult thing to deal with is the pins. If you have a clock that comes into your FPGA from outside the FPGA and you want to connect it up to a PLL, it turns out for the two PLLs in this chip, there's one and only one pin for each one of these two PLLs that you can use to directly connect the external clock into the PLL inside the FPGA. And again, they don't tell you what it is. They let you know if you use their software, which I can never get working on Linux because it's a 32-bit build and I don't think it's been supported in like a decade. I don't know. I could never get it to work. I don't actually own any machines that run Windows, so I have trouble with that. Now, I know that their software does work, and it does let you know if you're doing it right or wrong or whatever, because I've talked to other people that use it, and I've had them check for me various things, and this is why I know which pins to use, okay, for these inputs. So that'll come back when we look at the block for the PLL in a minute. In any event, the point is that these things are physical inside the FPGA. They're only connected in certain ways, and if you're going to use them, you got to play by their rules. And unfortunately, with hundreds of pages of documentation, they never bothered to tell you all of them. So I'll try not to rant too much more about that. So what do we got here? We got input sources to the GBuff. Can be an input, a programmable interconnect, a PLL output, which gets us in our ballpark, and a programmable I/O block, which means a physical pin, strobe generators on some devices that we're not using, and some other things as well, okay? So what we care about is this when we're dealing with the GBuffs, which really don't pertain to our current and immediate concerns, but this does, okay? We want to be able to hook up the PLL to whatever we want inside the FPGA. Now, normally, all this junk about the global buffers can be inferred when you compile your design. Now, the demonstrations that I'm going to give you today are pretty simplistic. I'm not sure if the Yosis tools that I'm going to be using are going to be able to even figure out that I'm using it for a clock in my circuit, because all I'm really going to do is fire up the PLL and then kind of send it out a pin so I can watch an LED flash. So I don't know if there's enough circuitry in there for it to statistically analyze the situation and figure out on its own that it probably should route my PLL into one of these global buffers. All right, so we'll have a look-see at that while we go. Maybe we can fake a circuit or something to have enough going on where it says, this should be on a GBuff. Or we can, I'll also show you, by the way, I have an example where we physically, manually configure a GBuff to be used from the PLL output as well, all right? What does it say? In ICE40HX to use a global buffer, use this thing if it is not inferred automatically. So this is exactly what I'm talking about. If it's not inferred automatically, you can manually do it. And I got an example with and another example without. So you can figure that out as we go. So what do you got here? If you want to create a global buffer, you can do this stuff, and you'll see me do that later. There's so much commenting in here, it's hard to see what's going on. But you basically create an instance of a SBGB. You name it what you want, and you give it these parameters down here, which is the clock signal that you want to connect up to drive the global buffer. And then over here, you want to say, what is the name of a wire signal in my module that I'm going to use that represents the output of this global buffer, okay? Now they talk a lot about, these global buffers can be used for this, that, and the other thing to let you optimize your bigger picture circuits. We can talk about this some other time. Right now, all I care about is the PLL, all right? But, look at how much of the documentation is the GBuff. I'm on page 8. That's 25% of the way through. Table of contents, maybe 10%, 15% of the document yammers on about the global buffers. So that should let you know that there is an issue here. You may want to know that this is a thing, okay? Again, it only really applies to more complicated circuits. So when I first got into this thing here with the ICE40, I was a little confused about what they mean by the two sets of outputs. This is not as simple as you think. Take their words very literally. You'll see, yes, it has two sets of outputs, but you can't, they're not arbitrary. Okay. Overrides user synthesizable clock frequencies and custom delays. So that's what we're going to do with this thing. Lattice has two software packages. One's called IceCube2, the other one's called Radiant. And you can use it to, compile your Verilog and stuff like that, and your VHDL, whatever language you want to use. And it's a GUI thing, and it gives you some nice screens, and you can see them later in this document. If you're into, if you want to program by pecking things with your mouse, that's what those tools are really good for. But, with all due respect, these also are built by the manufacturer of the FPGA, and they're pre-configured to guide you to not make mistakes that I've made. And when I think that I can hook a PLL up to any old pin I want, because the menus become enabled and disabled, and it says, here's the only pin you can use and stuff like that. It's buried in this software and not so much so in their dock, in their printed dock. And yes, they can help you quickly configure the desired settings if you actually have any idea what you need and how you're supposed to achieve that goal. And this is one of the problems when you have this super user-friendly thing that helps you make these choices and so on. But if you don't really understand the choices and the impact of those choices, which you can only get by reading all these documents here, then, is it really that much easier? I know people that have the GUI software and they don't know what they're doing either. So they can get a design that will go and do something more easily. But when you really get down to the nitty gritty, it's sort of like, you got to roll up your sleeves and get in the dirt and really understand what's going on if you want to use anything other than the most basic things here, okay? All right, so what do we got? Multiply it, you can divide it, and you can play around with phase alignment. This is the block diagram that I think I showed in another video when we were talking about the IP blocks. What you've got is this, see where it says voltage controlled oscillator. This is an analog device. You got a low pass filter, that's an analog circuit. You got a phase detector, this is going to be an analog circuit. And then you've got some digital stuff that happens around here. So what you're doing is you're controlling this analog circuit where this is your multiplier. and then you feed back in here to a divider, and what you've got is a thing that compares the frequency here against the frequency there, and when it's wrong, it tells this VCO to speed up and slow down. All right, that's what's really going on. Do you really need to know this? Not that part per se, but you need to understand that you got a multiplier and a divider, because you have to come up with the values to tell the multiplier what number you want to multiply it by, what number you want to divide it by, and those have constraints. Now, fortunately, even, us, doing the whole command line thing, have a nice little tool that was provided with Yosis that allows you to jockey all this together and just say, look, I want 65 megahertz. What values should I put in here? And what do I set these other things for? And it's really useful. But as you'll see, if you want to use a global buffer, you got to kind of then tweak it, and you got to understand what's going on, and that'll be a great example of why you need to look at both of these documents too, because neither one of these really on its own gives you the full picture. Okay, so we're going to ignore the phase shifter and the fine delay, other than I'll point it out because there's a nice picture right on the next page, I think it is, about how that works and how you set it up, or maybe later in the document. The point, what this really is you have the option of delaying the signal as it generates this feedback loop to generate the right frequency and the right phase. And I think there's some diagrams in here. We'll show you the phase issue a little bit later. The point is, you can set this so that the leading edge of your clock relative to the source over here can happen earlier or later in reference to, this reference clock, so that you can cause, various delays and timings and the order of operations to happen in an absolute known way if you get into a design where you've got super fine details and needs for that kind of tuning, okay? So, I'm sorry. Here's the delay adjustment. I was pointing at the wrong thing. But, all right, so you'll see a couple of diagrams that talk about that. And you'll see where you can put these numbers and say, I want to delay this, 3 nanoseconds more than it would normally be when it comes out of the output over here, okay? All right, so in here they name all these pins and tell you kind of what they're for. And I'm not going to get into all this. I'll let you read it. You can see there's a lot of stuff in here. And this is why they want you to use their configuration software. And this is why I am going to use the Yosis configuration software. Because, like I said, I know there are various limits and boundaries. And this thing delay compensated by this and blah, 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 especially as a hobbyist. This is a little much in there. I take my hobby pretty seriously as it is. Right? Oh my gosh. All righty. So what do we got here? What do we need for the clock input requirements, right? What do signals have to go into the PLL? All right, it wants a single frequency reference clock input that's going to run at a constant rate, okay? Reference clock must be within the clock frequency range. So like I said, this is the, one of the constraints that you're going to bounce around all over the place before you find out it's some number. 25 megahertz is in the range, as far as I know, and that's what I've been using for several years. I'm sure it's fine. At one point, I know I looked it up. I can't remember what the range there is. Reference clock must have a duty cycle that meets the requirements specified in the data sheet, whatever that is. It turns out ours is about 50-50, which is, optimal, what you really want. But if you end up with it high 1% of the time and low 99% of the time, that may not work. But, a crystal can oscillator like I'm using is going to be fine. Jitter. Right? That's related to, does it run on a constant frequency? Does some pulses wider than the others and so on? I mean, yes, they always will be. Nothing's perfect. And there's some specs on the data sheet. I'll leave that as a task to the viewer to look all that fun stuff up. Crystal can oscillator at 12 megahertz, 25 megahertz, 50 megahertz, even 100 megahertz should be perfectly fine for this, okay? The output requirements, again, you can only be, a certain range of frequency. You can't generate 4 terahertz or anything like that. And it also has to run greater than 0. What else we got? PLL out is not valid until this output remains high. Now, I haven't really used this in my designs. As I move forward and do more complicated ones, we might want to integrate this signal into the reset logic in the system. Because what happens is, these are analog circuits and they're charging, capacitive elements, ramping voltages up and down. It takes time. Several cycles of the clock have to go by. Could be hundreds, could be millions of cycles have to go by before the output of this of that whole system is known to be stable and running at the right frequency. When it gets there, it will let you know with this 1-bit output signal that I glossed over and scrolled by a minute ago. All right, so it tells you down here, it multiplies and or divides the signal and generates an output, okay, and uses this math here, and you can do this, and +1, blah, 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 so 0 never works. You don't want to divide or multiply by 0, in other words, so it's always +1. These are the variables that go into the design, and we're going to get them from the tool that will generate what we want. Here's what they mean when they're talking about the quadrant, phase shift, and all this other stuff. There's a couple of bits that you can configure that says I want it 0 degrees shifted or I want it 90 degrees shifted. So that means this. If here's your reference clock here, and it's running, it's high less of the time than low. This is not a 50-50. It looks like a 40-90. The duty cycle of this thing. Well, the output of the PLL, if you actually run it at 1-to-1, you multiply it by 1 and you divide it by 1, and the output of the PLL will be the same frequency as the input, but it will be a 50-50 duty cycle. So that's useful. All right. Now, if you want, you can set a bit in the design and say shift it by 90 degrees. So then the output will actually be over like this. And if you use 2 outputs, because it has 2 outputs, one of them can go like that, another one can go over like this, and you can play all kinds of games with DDR. This looks like quadrature type signal. It depends on what you want to use, your design for. So these were easy for them to provide, obviously. So it's part of the services that you can use. I don't normally use this, but it's good to know that it's there if you find the need for it. Okay. Now they talk about the fine adjustment. I can go from 0 less than n less than 15 delay taps. What do we got? 16 delay taps of 150 picoseconds. All right. So this is very finely tuned when it comes out of your oscillator, the PLL output here. Okay. It just goes through a bunch of non-inverting buffers. And I can say, I want to look at the frequency right out of the PLL. And that'll be lined up really nice like this. Okay. If you're multiplying and dividing by 1, it will be. All right. Now, if I start tapping off over here further later, it'll start delaying it sort of like this, right? Depending on the frequency, I doubt you could get a 90-degree shift, although only 16 of those. That's a pretty high frequency to achieve that, but it moves the edge back is what's going on, all right? So again, more things you can tune. Nice to know that it's there if you need it. I have yet to need it, and I'm not going to get into the details other than mention that it's there. And also, I'm going to observe, again, that this is a really simple PLL. If you go grab a more modern, bigger chip, a lot of times they'll call it a digital clock manager or whatever other brands might refer to this thing as, and they can get very sophisticated, okay? So just be prepared for all kinds of cool options and features in other circuits, but also keep in mind that in the end, if all you want to do is create frequency A from frequency B, there's usually a simple way to do it once you know how. All right, so what we can also do, low power mode. You can obviously shut the whole thing off. I think, if you're running on batteries or something and you're not going to use it, you can stop the oscillator from running, which saves you power. And this is really what happens on, modern CPUs and your computers. This is why they heat up when you're using them and cool down when they're not in use, because they actually have these PLLs and stuff built into all modern CPUs. Have these things. Even these tiny little $1 socks will have these. And it makes it very difficult to get them booted up quite often. It's just like this, just to get out of reset on even, a $1 or a $2 ARM sock, because you have to deal with all this sort of stuff. And the chips, my point is, the chips can stop themselves when they're idle, and then an interrupt can come along later and restart the PLL and all this other fun stuff. So you can play all kinds of games with this. I'm going to ignore it and let her fly. Here's their graphical stuff, how to use their tools, what to click on, and here's an example on how to use it for a chip that I don't have, and how to select all these options. And at this point, you should be able to recognize what you're really going to be doing with this thing. So it says here, you pick, the chip you're going to use and say, I want this PLL. How many outputs do I want? What's the input frequency in megahertz? And then what is the output frequency? And in the simplest case, you hit go, and it'll just generate it for you. And then they're going to talk about the parameters for that graphic tool. And blah, 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 right? Okay. And then what do we got down here? Radiant supports this device constraint. This is the other tool. This is the Radiant tool. The other one up here must have been IceCube. I didn't look that closely. Blah, blah, blah. The PLL Manager. New project. I don't know. This is probably... No, that's Radiant as well. I don't know what this other... context is for the other diagram down there. What does it do? It generates 2 HDL files, and it's going to put this, that, and the other thing. We'll get the same thing with our simple little command line jobby. And then it says down here, it says once it has been created, here's what you can do to use it. Is that what I'm looking at here? PLI out A is a gen clock for ×4. So if I get 25 megahertz going in and I set it to ×4, I end up with 100 coming out, kind of a thing. I don't know what this notation is. It must be some of the data files that go along with their tools and stuff. And we've seen this, Yosis generates all the same stuff. So here's how many PLLs you use, how many LUTs, and all this other fun stuff. Here's the IceCube 2 diagram, and I've seen this. I have actually gotten this to run many years ago on Linux, but it was enormously difficult. Nothing worked at all the way they said it did. Their license manager was the thing that prevented it from being useful in any real way. It took several afternoons to just get it to do the basic thing, and I threw it away and said, I'll come back if you ever come up with one that works on the platform that I'm using, that is. It'll do all the same stuff with different kind of windows. And we're going to see this in a minute. Do I want to take the I/O pad? That's the pin. Am I going to feed the PLL from a signal that comes in on a pin from the FPGA? Or am I going to run the PLL and take in a frequency that comes from something else inside the FPGA? So that's what they call a core, is when the input is coming from circuitry that I'm going to design, some Verilog maybe in the FPGA. And the pad means I'm going to just take in a frequency from a physical pin on the device. Okay. Today we're going to focus mostly on core because of the mistake I made when I built my board. I connected it up. My oscillator is not connected to a pin, a pad that can be directly connected to the PLL. All right, so what I do is, you'll see in a minute, the free running clock frequency goes into the FPGA, and then I simply route it through the FPGA and then into the PLL, and I configure the PLL as with a core input. And the tax for that is that I waste one single LUT in order to make that happen, which for my cases is a non-issue. It's perfectly fine, but it would be nice to be able to use both options And it would work that way if I had it connected to the right pin. And you should connect yours to the right pin in your designs in the future. Now they talk about the feedback path. This has to do with if you're going to get super fancy and you want to take care of that yourself. And this is the logic that has to do with the multiplying and or the dividing. Usually it's the dividing. So when it says I'm going to generate this reference frequency, I could divide it by 4 and feed it back in, and then it would have to run 4 times faster. That's how they do the multiplication. The multiplication is an artifact of the division to some extent, okay? That's one of the ways it gets multiplied, is my point. Do you want to dynamically control the delay? You want to change the delay over the course of time, and you would choose this because it will generate a different set of configurations for the hard macro, the hard block, the hard IP that you're setting up with this setup wizard thingy, so that you can send in a 4-bit number to control that mux. I'm not going to scroll back. The giant mux with all those little buffers, to select which buffer it is, so you can dynamically, on the fly, change your delay based on your FPGA logic, if you want to. What else? Here's your 90-degree phase shift. So if you didn't look at the other pictures and didn't really think about it for a minute or 10 or 20 or however long I've been yammering, you would have no idea what any of this is for. Okay? So they're going to hit you with a barrage of yick, and you're not going to know what it means until you kind of look in here and kind of figure out what's going on. Create a lock output port. That's that lock signal. Are you going to use it or not? Create a bypass. What's that all about? Well, it turns out a bypass is a thing. If you look again at the diagram, there's a line that says, when you take your input frequency and the PLL output was over here, there was a line that wrapped up right around and let you just short circuit the whole thing. And that's this bypass. And you can control that as well. There's a 1-bit input, I believe, that you can turn it on and say, just don't use the PLL anymore. Just run off the raw clock that's coming in. So you got all these controls, all right? And then it gives you a summary and select the number of this, blah, 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 blah. Okay, so I suggest you skim through this and get more familiarized with the bigger picture of this thing, if you're going to do anything more than just say, I want to convert clock A to clock B. Now, this is really why we're here, and this is the big thing we got to get out of here. Now, these 4 bullets here are either the same or a variation of the notes that I put in my README file under the PLL examples is referenced. So this is down here, okay? That's what this is all about. To remind me that these are the physical pin constraints. Somebody on the internet posted this. By the way, here's are the pins if you want to use the pad to run your PLL and go directly into the PLL. You got 49 is the only one that'll run one of the 2 PLLs. And 129 is the only pin that you can use to run the other of the 2 PLLs. Any other pin, you end up with the problem that I have right now, and that is I can still build circuits and it work fine, but you waste 1 LUT because you're not able to connect the input clock directly to the PLL. All right, so it's a little bit embarrassing. I have not verified this. I have verified this. Okay, we can do a quick test. We can't see it run on my board because I don't have an oscillator hooked up to this pin. We could rig one up, I suppose. But there's another way to do it. When you compile your code, if you try to create a pad and you say connect it to pin 150 instead of 129 or 49 or whatever, then even Yosis will say you can't do that. It's unfortunate that it doesn't say, by the way, try one of these, which is why I put this note here for future reference. Okay, so if you want to use an external clock, most of the time you do. For a simple hobby project, you got an oscillator, you want to just change frequency, just connect it to one of these 2 pins. If you're using an HX 4K chip in the QFP package, and you should be fine, okay? Let's talk about these guys, because that's really what's we're going to do now. So now it's just a matter of configuring them up. Let's have a look, see, I guess, at these 4 bullets real quick. What do we got here? Some additional things, the user guide, blah, blah, blah. We were just looking at that. And this is in section 5.1.2. I don't know if that's the same release. It is the same release of what we were looking at. So that might be a literal copy of this thing. My point is, I think this is updated from time to time. They could change some wording in here or something like that. Okay, so what does it say? Any instance of a PLL is placed in location of the I/O cell, and that means, you know, one of these pins. Then an instance of an SB global buffer I/O cannot be placed in the same cell. Okay, so if I create a PLL and I'm using this as its input, I think, yeah, then I cannot hook this up to a GBIO and use that pin in my circuit. So it kind of hogs the input, is what this thing says. If you put a core, a PLL core or 2F core, an instance of SBIO is in output only mode, could be put on the associated IO cell. All right, so this is the stuff that I had a hard time understanding, you know, when I first started doing this sort of thing. So they talk about this associated cell. Again, we're back to this crap up here, okay? Now, if I'm using a core, and a core, like I said before, means that the PLL is going to read its input clock signal from something in the FPGA. In other words, not going to read it from a pin. Then, in theory, I could use the pin for something else. And I've actually done this. But if you do this, that pin can only be used as an output from the FPGA. Okay? Because obviously the PLL is somehow consuming the part of the input logic that's inside that I/O pin logic. Okay? What does it say down here? If I use a pad, in other words, I'm going to configure a PLL to read directly from the pin that's dedicated for that PLL, either 49 or 129, whatever one the PLL binds onto. Then, what am I going to do? The associated I/O cell cannot be used at all by an SBIO or a GBIO. Basically, if I'm using the pin, don't try to use it for something else. And it says down here, if I'm doing a 2F core or a 2F pad or a 2 pad, then I can use an SBIO, an output-only mode, in the right neighboring I/O cell, which is a whole nother thing. They don't really, usually these are in pairs. And you know, the G buffs, there's usually 2 pins next to each other that are a G buff pin. This may be referring to the other one of the 2 that are physically next to each other. And it may have to do with the fact that the pins are usually paired together on an FPGA on some of the I/O banks so that you can gang them together and use them in a DDR type configuration. And that, I'm just theorizing here, okay? Why in the world would there be this relationship? Well, it turns out there oftentimes is, and there could be some circuitry that the PLL prevents you from using. And you could end up in the situation where, just like up here, you know, if there's a PLL involved, then you can use the pin, but you have to only use an output-only type configuration in the pin as well as its neighbor. Because the neighbor, like I said, quite often will have some like DDR type stuff going on with it, all right? So there's a couple of these rules and constraints. And hopefully, you know, now you've seen all this, you don't need to understand it all right now, but you need to have heard it, is why I'm beating all this up before we dive in. Because if you don't, and then you're doing something, and you're going to be asked to make a decision, how do you want to configure this? Well, then all of a sudden you remember, oh yeah, there were these rules. So now you know where to look them up, and you know at least that they may be related in some way, okay? So here's a technology library document, and I just noticed that they updated it just a few months ago. So it's always a good thing to go back here and see what they changed. And what they changed is political correctness, added some definitions of stuff and some sample code for VHDL, and talked about the answer database on the Lattice website. So nothing of consequence right now. So if we go down through here, the table of contents, we find the PLL primitives, and I showed this once before on my channel. Now, what you need to understand is there's several different ways to do these things, and there are cores, which I've already hit twice, and there are pads. If you're going to use a pin, you need to use a pad thingy. If you're going to provide the reference clock from inside the FPGA, you use the core, okay? You can only use the pad when the pins that you're going to connect the this reference clock to is the one and only one pin that you can connect it to for each of, in this case, the two PLLs. So it shows you these are the signals that you care about when you configure a PLL to operate as a core module. And basically what you've got is your reference input clock. You got this lock output to let you know it's okay or not. Is it running correctly? And then you've got these two outputs, which, be careful how you hear that word too, okay? This is one output that can be connected to one of those global buffers, or you can take that one output and connect it to core logic, just regular old routing logic inside the FPGA. If you're going to use the PLL to generate the clock to run a bazillion LUTs, you want to connect it up to this one, okay? Then here's your bypass control. You can stop it, reset the PLL. Then you've got these fancy things that I don't use at all, which have to do with the extra divider you can put in there and your delay controls and things like that, okay? Well, it does give you a rundown, and it reminds you that, if you're going to use for regular routing, then that comes from here. Otherwise, you want to use the global one. What else we got that's interesting at this point? PLL out global and core with respect to reference client dynamic delay part. Controls are enabled when the delay adjustment mode is set. Okay, so there's a bunch of, if you want to play with the fancy features, you got some reading to do, okay? Then they talk about the individual parameters and what they're all used for. I want to make sure that you understand that this document should match the other one, but they don't. Because the other one that we were just looking at does not talk very closely at the pad style things. If you're using core, you will see, what do we got here? These are the parameters. Where are the IO? When you configure these things, there are parameters, and then there are like wire signals that go in and out of the block. This is not documented in the most pleasant way. Ports, I see. Here's the ports. They document these in a big morass like this, and then the parameters are documented in a nice little table. Thank you very much. Okay, I was just looking at them for crying out loud. Look what we got here. This is called a reference clock. When you use a core, the input is called a reference clock. When you're using the pad, the input is called a package pin. All right? Now, if they would have called them both the same thing, would that have been so bad? I don't know. I suspect they have different names because these may not really be different modules. It might be one module with all the stuff on Earth in it, and these are the only ones you use when you want to use it as if it was just for a pad, okay? That's probably why they have different names. But, and you'll see why that's a little bit annoying in a minute when you're playing around with our code, when you're making examples. So again, you get the pin versus the pad. But all the other stuff, I believe, is pretty much the same stuff. You've got the core versus global for the output pin signals. ports, I guess we could call them, out of the block. Okay, so you got two different names for how you get stuff in, two different names for how you get stuff out. Two different names on the input have to do with whether it comes from a pin or a routing fabric. The two different outputs have to do with whether it's going to be global or just some local routing. Okay, so that's the main thing you really want to get out of all these things. The two pad. All right, so the first two that we looked at, I would argue, plain, simple, should be within the grasp of a general understanding of what I've talked about so far. When you get to these two thingies, we're getting into this thing where you have two different outputs now. Notice you got global A, core A, global B, port B. The A and B are the two different outputs. And you remember I stopped myself because global A and core A, yes, those are two ports, but they're the same signal. So this is one of the outputs of a two-output PLL, and this is the other one. Now, I wish they would have just said it plainly, but they don't. If you use the two-pad, what you get is kind of a copy of the cleaned-up input as it is, same frequency, and you can get the output of the PLL generated, multiplied, and divided signal out of your block here. So what does it say here? Should be used when the source clock of the PLL is driven by an input pad that is located at the bottom IO bank, bank 2, or top IO bank, bank 0. In other words, it's driven by the one and only one pin that can drive it. There are no other options in spite of how they phrase this. And in addition to the PLL output, the source clock is also required. In other words, if I wanted the 25 megahertz that I have hooked up to my FPGA, in addition to the PLL generated frequency, I could use this. And this gets you around that problem that it talked about earlier. If you're using the pin to run the PLL, you can't steal the signal off the pin and still use it. Well, if you use this, you can, because the PLL will propagate it out for you, okay? So you can take the raw input frequency as well as the output of the PLL. That's what that one's for, okay? And you go through all the how to set it up, blah, 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 blah. Then you get the 2F core and the 2F pin. Core, you're running the clock from somewhere in the FPGA. Pin, you're getting it from a physical pin on the one and only one pin that the PLL can use. And this is used, and they speak with great general terms here, generate two different output frequencies, and the source clock of the PLL is driven by routing, because that's the core part of it, okay? I can get two different frequencies. And I thought, wow, that's awesome. I could get to, I want my 25 megahertz, 42 megahertz, whatever. No. Yeah, you can get two different frequencies, but you don't have much option as to what they are. So what happens is, if you do this, one of the frequencies is the frequency that you configure it for. The other one, and you'll see that in the parameters, is simply the same frequency divided by 2. That's your only option. For your second frequency is going to be half the frequency of the first one. And that is hiding down in here where you see this fixed blah, 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 half. Okay? So what happens is, if you want half the frequency, there's your second frequency. Your first frequency is the one that would normally come out of the first example of the core or the pad one, the first two that we looked at, all right? So if you use the two frequency, don't cry because you can't get two arbitrary frequencies. You can only get X and X over 2, all right? In addition, you can still play games with the phase shift and the other things, but the frequencies are going to be X and X over 2. And that's what they mean by all this. So here's the same thing, the 2F pad. We were just looking at the 2F core. The only difference between the two is I'm getting it from the pin instead of the routing logic inside the FPGA. All right, so that's the big picture. Let's look at some code. This will go nice and fast at this point, I hope. Example 1. These are created in two different ways. Let's make sure I got a clean build here. Get log Where are we? This is the make examples because this isn't parameterized just a few minutes ago to record this video, blah, blah, blah. We're all good. Get status. I think I got something that I never committed, playing around with a PS2 mouse, but other than that, it's all up to date with the repo. So look at what's here. See these two guys here? These are the PLL modules that have the hard macros in them. And these I hacked myself by hand because, among other things, I'm going to show you how to use the gbuff output thingy. With the tools that come from Yosis, you have to do this by hand, as far as I know. We'll look at another technique without the global buffers in the other example. So I got a couple of bases covered here. So let's look at, what do we got in the README file? To make sure I remember to tell you what I'm supposed to do. What you can do is you can run this ICE40HX thing, and that's what I'm talking about. I can run this command, and I can generate my Verilog code and be done with it. Input frequency is 25. Output frequency is 50. The P means I want to generate one of those PLL pad blocks. And I want to get a 50 megahertz from a 25 megahertz directly off the pin. I don't remember what M does. ICE PLL help or something. M. Save the thing as a Verilog module. Yeah, generate a Verilog module. Because if you don't say this, what it'll do is it'll just say, here are all the dividers and multipliers and all the values you need if you're going to instantiate a macro and write some code. This says, write the code as well. And by the way, name the module this. Okay? Here's one. The only difference here, I think, is that I got a P there and no P on here. So here's the one that this will say core. Now, if you run it, and I don't have the -F, what'll happen is it'll write it to the screen. So here's what comes out of this tool. It says, hi, I ran this, and the usual warning, you get what you pay for. I want to go from 25 megahertz. I want to go to 50. And then it'll tell you, due to the constraints, the PLL, the multiplier and the divider, and all that other fun stuff, this is as good as I can get. Well, it turns out multiplying by 2 and then dividing by 1 is pretty easy to do, and you can achieve 2x for your output. We'll see one in a minute that doesn't do that. So what does it do? I said, not only do I want to know what you can do, I want you to actually write the code for me and make a module. And you saw, I said, name it that. So that's where this comes from. And it's going to generate a clock in, clock out, and a locked signal coming out of here. There's the PLL core that you saw in the documents we were just looking at. And then the blah, 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 right? What's the divisor? What's the multiplier? What's the thing? What's the filter? Blah, blah, blah. All this is based on the analog settings that you have to choose in order to get the VCO to run at the right rate. Then the output and input wires that go in the ports in the module are connected down here. So you have a reset that's hardwired. Bypass is hardwired. So in other words, I don't have like a way to reset it from out here. When I instantiate this module, I'm not going to be able to turn it on and off. I'm not going to be able to bypass it. It just didn't pin those out. This is just get it to go. Here's the in, here's the out. Let me know when it works, and I want these relationship. So the reference clock is my input, and the output says PLL out core. And remember, core means just go to the regular old routing fabric. I'm not using the global stuff. Okay? Now, what I did is I ran this, and I saved it in a file, and then I edited this file. So you just look at that one. Now look and see what's in this file. This one here, what did I say? I wanted 40 megahertz from 25, and the best I can do is 39.844. And you'll notice that this thing, the comments in here look different than the one that I did up here, okay? This might have been done on a newer version of the ICE PLL that I have on my Raspberry Pi right here, or an older one, I don't know. I don't recall. But the point is, if you see these things around the internet, you see these various things. And it's going to tell you, here's the parameters. And I said, generate the code. So I'm going to I don't have to worry about figuring these out. And also this one tells me, FYI, the VCO is running at 637.5 megahertz, by the way. So that's kind of cool. Okay, it's really hauling there. Okay. And then you get the in, we got, in this case, the global clock, because I hacked this. And then we got the locked signal. So what I did is I added this down here and did what the documentation said. And I left commented out if I want to use a core rather than the pad. So I have like both in here all at once. Remember, if you use the core rather, you get a reference clock. But if you use the pad, you use a pin. Okay, so this is kind of commented up as an example of, this lets you do it either way. I can either do a core or a pad, and I can take the output, and notice it's coming from PLL out global to this wire here, which I then send into that one line of code that you saw in the manual. That do this if you want to have a global routed buffer. And I want to force it to do that in my design. Put this in here, and then so you say the PLL goes in here, and then the output from the global buffer goes there, which I connected up there. Okay, so there's that one. Let's look at this other one. I don't know if I did that on both or not. Yes, this is the same thing, but I don't know why I chose two different frequencies. I guess to have one that came out right and one that came out close. And I did the exact same thing, but this is the core rather than the pad. And you can see how I changed it to use one versus the other signal. Again, that matches the doc, it matches the discussion and everything else. All right. Now, when I compile this, there's a counter. We've seen counters before. This is a parameterizable counter that simply says count free running counter with this many bits and send it back to me. So I can just create them at will. And I got to put a parameter that says here's how many bits I want in there and get the noise out of my source code. So what we saw there is I've got two different PLLs, one running at 100 megahertz, one running at 40. One of them uses the core, the other one uses a pad. And there's a top level module that I can then use to generate a module that has that PLL in it and connect it up to a bigger design. So I've got a 25 megahertz oscillator coming into my FPGA. I've got a reset button, and I've got my 8 LEDs. That's all I've hooked up in here. I'm going to say I want a 30-bit counter and a place for it to go. What do I got? Here's my PLL, and I'm going to give it 25 megahertz in. I'm going to take the output, which is a 1-bit wire, called PLL out, and I'm going to take that PLL out and I'm going to put it into my counter for the clock for the counter. And the counter has a reset input and it has an output of so many bits wide, which is this, which I set to 30, which matches that. So when the counter output comes out, I can take the most significant 8 bits of my counter and hook them up to the LEDs on my FPGA. And now we can think this through. If I have a 30-bit value, that's 1 billion. Roughly speaking, that's 1 billion. If you count into a 32-bit binary number, it's about 1 billion. So what I'm doing is the most significant bit of this counter here will go, will flip at the input frequency of the counter, which is supposed to be 100 megahertz. Divided by 1 billion, so that should take 10 seconds. If I did all the math right in my head while talking, which hardly ever works, right? So that should run relatively slowly if we make it and program it up on my board. Assuming that this actually is set for 100 megahertz, which I may foolishly not have done. Okay, yes, everything maxes up. If I make world, the whole thing will compile. Let's have a look-see at the build. Let's see, error. Sometimes they have a capital letter, ARNING, which is quite often when I'll search without the first letter. Network combinational, that's a standard warning that we get all the time. So I have no warnings, no errors. Max frequency for PLL out. is that for that module. So we talked about this, I think, once before when it talks about timing tests, and I should set this more accurately when I do my designs. We can talk more about that at other times when we're doing something more real and serious. So if I type make prog on my system, I'm on my Raspberry Pi that's plugged into my FPGA eval board. This will just simply program that into the FPGA and reboot it, and it should start counting on the LEDs, which we can see here if we kind of count it out. 1002, 1003, 1004, 1000. Yeah, it does look like that most significant bit goes on and off once every 4 seconds or so. I'll leave it as a task to the reader to count the number of video frames on YouTube and let me know how far off I really am. Hopefully, not too far. All right, so the files in here are kind of like a superset with references on, kind of what you need to do for A versus B, and by that I mean the core versus the pad. Now, because my oscillator in my FPGA board is connected up to pin like 53, I think, 52, rather than pin 49, I cannot use a pad design. I can't do this. I have to use a core because I'm not on the right pin. So let's say we do this by mistake. This took me forever to understand the first time it happened to me. What is going on here? Okay, so if we want to do a pad, and I made a boo-boo, and what I wanted to do was look it up. It's PLL 2540. If I use that one instead of the 100, because the 100, remember, was set up to be a core, and I do this instead. Otherwise, this is the same. And now I got to list the other thing in here. Actually, I think you can just put them both in here. And what it'll do is it'll compile it all, but when it's done, it'll say, nobody used this one, so I'll throw it away. Normally, you don't put extra source code in if you don't want it, but it should be fine. Now it's going to gripe. It's going to say, look, I can't do an SBIO to a PLL, blah, 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 blah. That's what this means. Okay? It took me forever. Error number, whatever, and make rules. Let's see what the errors really are. Let's clean it up and start over. I always put a make world in there that does a clean and then a whole thing all over again. So we can search for error. Wow, that's it? 2 errors, huh? Are they capital? Error. That's it. PLL, let's see, package pin SBIO clock 25 blah is not connected to a PLL bell. I forgot what BEL stands for, but it's a thing, and you see it in their document. You see all these BEL. That is, I think, the name of an interconnect. In the lingo of FPGA configuration files and the names of their thing, the LUTs and the latches and the flip-flops and all this other fun stuff. That, I think, it might be a basic element or an input or something. I don't know. Look at the comments below. Somebody will point it out. I looked it up once. It slips my mind at the moment. Anyway, so what that means is I don't have this signal, the clock 25, cannot be connected to any PLL. Period. Because it's not on one of the magic pins. Now, if we do this, and we put it on a magic pin, it will work. But because I don't have a clock on that pin, if we run this, the thing will sit there like a bump on a log and not do anything. All right, so if you do this, you need to have a clock on pin 49. On this design, I think pin 49 is just connected to one of the headers that's floating. So that won't run, okay, because I don't have a clock hooked up. But this one, if you can get the clock to go into the PLL, it will work. But if you hook it up and it cannot connect it, that's the error you get, okay? So let me make sure I don't leave my files all broken. I should probably commit it like this so that you don't have to hack up the files if you want to reproduce this at home. Git diff, oops. Let's have a look, see. So all I've got in here is I've included both the modules, and I happen to know that's perfectly fine. If you don't use it, it throws it away. And I left this thing commented out down there. I'm going to go ahead and push this. As seen on YouTube. Oops. It's ass seen on YouTube. All right, whatever. I'm not going to correct. Yes, I know I can correct the message, but it's funny. I'm going to just leave it. Well, let's look at this second example now. Okay, here we go. This one is, let's clean up the mess. Look what we got now. You'll notice that these went away. So let's start from scratch. Look what's happening in here. In my make file, this is basically the same example we saw before. It includes the need for these two files, but they're not in the source tree. I put those ICE40HX commands in my make file. I'm going to just generate them when I type make. Okay? This gives us a little bit more configurability. However, because the ICE40HX command, as far as I know, oops, does not have a way to say use a global one. Let me grab on, let me log off it. Oops, let me open a window here. This is my desktop machine that has a newer version of the tools in it. All right, we do have more options. See, this one, those are all you've got. This one has a few more. But I don't believe any of them include the global thing. I hacked that in myself. So this one is the -P option is what it has. My older one on my Pi, I can't even do a pad. It only does a core, for example. So if you're going to use these old, these open source tools, you may have to do a little homework on your own and add or tweak some of those ports is my point. Oh, this one has this find the best thingy out of this list. And somebody provides a list of the standard oscillators you can buy at Mauser, for example. It says, hey, look, just give me as close a frequency to what I asked for, and you can use any input frequency. I don't care. I'll go out and buy an oscillator that doesn't suck for my purpose and just, and then just pick the best one for me, because they're all going to basically cost the same price anyway out of the list of standard oscillators, and it provides a way for you to provide your own little database and say, oh, I can use any of these. That's kind of neat, okay? But it also has this pad option, so we want to generate one for the pad versus the core. That's what you want this for. This was done in 2018. I don't know where the Pi people are in their latest software releases. I think I might have an older image on this Pi. I'm sure I do. And if I rebuilt my Pi from scratch today, I might get a newer OS and newer versions of these files, or I can download them and build myself. I've done that before. In fact, this machine here, this X570, is all home built from the Git repos for Yosis and Ice Storm and all that fun stuff. So that's probably why that one is the newer one. In any event, this is the older version of ICE40HX, and it will always generate a core input PLL, which is exactly what I need on my board here. So if you look at the make file, it says input is the oscillator clock here, which is variable design right there. I want to generate 65 megahertz, and I want to generate 18.432 megahertz. And I'm going to generate these two separate files, and the name of the module inside the file is going to be called these. And yeah, I probably should have done the base stem name macro in my make file to prove that I'm some super awesome guy. Maybe, I don't know, I'll do that some other time. Because the point is you can get this name out of this variable and prune the V off, which would be like super cool, right? In fact, then I would have only one rule and it would infer it. You know, no. Yes, I could do all that, but it would be less obvious to somebody that doesn't know about all that fun stuff with makefiles. They just magically appear. Okay? So if I do all this fun stuff, the first thing that the make command would have done, we'll go back and look at that warning in a minute. I think it's that standard frag thing that we've seen all the time. First thing it did is it generated these two files by using the rules you just saw, the recipes. Sometimes they like to call them that. I can't get this. I think I've talked about this when I did my speed run CPM port to the Nouveau, because I use this frequency to run my CPU, and it's a little bit off, but close enough. And here's the values for that. You can see it's a core. You can see that it uses reference clock and not reference pad and so on. And it has a PLL out core, not the global. Okay? Because that's what the tool generates. You want another one, you get to do it yourself or go download the Lattice tools. This one I wanted 65. I got a 64.8844. This one I want to use in another project that I'm getting ready for, where I'm going to use the two PLLs at these two separate speeds to run the Nouveau processor, my Z8S180, and then I'm going to use this clock to run the VGA display in a 640 by 480 mode. Or was it 1024 by 768? I don't know. Stay tuned. It's a video coming soon to a YouTube channel near you. In any event, I needed these two frequencies at the same time in one design, so I put this sub-project together and used it for the basis of this video. So you'll see this again. It's all the same stuff with different values in here to generate the other frequency. So let's take a look-see at top. What's the difference? What's going on here? I got two separate oscillators this time. Well, let's buy the thing. I didn't realize it was that much junk. We get the pretty callers. So I got 25 megahertz coming in. I got the two buttons. I'm only going to use one, S1, as the reset to my counters. So what this is it's just two PLLs and two counters. But I don't have enough LEDs to show all the outputs from both counters, so what I've done is I've taken the most significant bit of each of these two counters, and I've assigned them to two of the LED pins. That's all. I set all the other ones to 0, so they're off because, or rather tilde 0. They have to, yeah. Remember, the LED goes on when the output is low. So you have to set it to a 1, and tilde 0 is all ones. So pardon all the dog barking in the background if that's being picked up, and I'm sure it is. Somebody must be approaching the front door of the house. All right, so what do you got? I instantiate each of the two PLLs that you just saw. I send clock 25 into each one, and these are cores, so that 25 megahertz clock wanders around in the FPGA however it needs to get there to go over to these two PLLs, and I get these two separate outputs. The clock 1 and clock 2, those are single bits, which actually come out of here. I had my scope hooked up to it a while ago, and I was looking to see what the thing looked like, and yeah, they measured out. Sure enough, they were doing what they were supposed to do. I'm not going to rig all that together right now, and besides, we're in overtime already, so let's move on. And in conclusion, let's take the most significant bit of each one, hook them up with the LEDs, see what happens. If I do a make prog, we'll see that happening. Now you can see the two LEDs going on and off. They are definitely not the same frequency, and it's not half of the other one either, because I set one to go at 100 megahertz. The other one's going at 40 megahertz. So there's a 4-to-1 ratio between the two oscillators, and I've divided them by whatever number of bits is in those counters, like 1 billion. so that they run much more slowly so we can see them with human eyes. All right, so the one that's going on and off faster is obviously the 100 megahertz clock, and the one that's going more slowly is the 40 megahertz clock. And we can verify that because the LED at the end of this row of LEDs is going to be bit number 0, which is C2. C2 comes from the what is this? We're not running. I confused this with the other example. I'm not going to go back and re-record this. One of them's going faster than the other. It's simple as that. This one's going around 20. This one's going around 65. You still now got about a 3-to-1 ratio between the two. The slower one here is on clock 2, which is the LED closer to 0. And the faster one is on LED 1, which is above the slower one. And that's exactly what we saw coming out of the Fpga. So, I caught myself a couple times. Let me know in the comments what else I may have messed up. Thanks for watching. I'll talk to you later. We'll see you on the internet.